what is going on? Well, first is the VP engineering. So the guy, he's been VP engineering for, Greylock back companies and Kleiner Perkins, and he's a hitter. He's had thousands of engineers under him. He has somewhat fewer with us, but he's a guy with serious chops. And his big focus is productization, is making software, into something that is viable, usable, and all that stuff as a service on the cloud. That's his big thing, and that is what he's pushing to get us to do. He doesn't have a clear timeline yet, but he's working through that. And I don't think there's another guy on the planet that I would rather have. And he's impressive as hell, as you will see when we can finally disclose who he is. So it won't be imminent. It'll be a few months because he's sort of working for us and his current place at the moment. But that will change as soon as his golden handcuffs are complete. So at any rate, and again, as I mentioned, the big focus here is the work we're doing with Microsoft and AWS and Viasat and Inmarsat, and as well as HPE and Intel. But the big thing, regardless of whatever, with HPE, Intel, and all those guys, where we can really ramp revenue quickly and scale is to have it on AWS and Azure. If somebody can go to those places, say, yeah, I'll buy it and I'll pay you for it, and here's the per whatever charge per gadget per month here for this much data, etc. I'll pay you this charge, and that's how you scale. That's how you really scale fast. Because I can tell you, there is a $50 billion company that says, if you could do that, we'll use it. And I've had other big, and that's like no like if, and, or but. That is a real, yes, I do that. But there's also tons of companies, like I could name Chevron, for example, that would, if I could say, here, all you have to do this is this SaaS thing, and it's already there on the major sites, the major cloud services. It's not hard for people to do it and then suddenly say, wait a second, wow, my bill went back down by 75%. So this is a meeting of our staff, right? So anyway, we're working on this plan. It's going to have KPIs. It's going to have a lot of specifics. We need to build this thing, and it's not slowing us down in the sense of we're focused on the SaaS thing. That's what we're doing right now, and fulfilling the requirements of DoD. But this is sort of saying, all right, that can't be everything. That's where all the focus is now, where we're bringing in talent, where we're really doing things. That is what we're doing right now. But where we really need to take this next, and what are the other things that we really need to develop that will generate value within the 18-month time frame? That's the questions we need to answer, and we are getting answered in this thing. It's going to be done by the beginning of October, and then the clock will start to run. So this is sort of more on what I was talking about before. So we've really been cheap before, and we need to start bringing in some heavies, like this VP engineering, like others that are sort of like really high level engineers. And so that's going to cost some money, and that's why raising $1 million or $2 million or $3 million or something is going to be, I would say, yeah, can we get along without it? Yes. But part of what you need to do with these high-end engineers is you need to be able to show them money in the bank. because they'll tell you, well, this is nice and everything, but you guys have 2 point whatever in the bank. That's not good enough. I want to see, 4 million in the bank or something. I mean, I want to know that you're going to be around next year, so I'm not leaving my cush job at Amazon and going to work for you guys, even if you're paying me the same, because Amazon's not going out of business, but you guys may. And so I want to see money in the bank, and it's all the top guys. That's the deal. So part of this is just credibility with them, and part of it is, yeah, we really, really want to have this money in the bank. The other thing is, we don't want to go into a capital raise, for 10, 20 million and say, yeah, we're almost out of money and you can squeeze the crap out of us. Well, no thanks. I mean, that's the way institutional guys do it, and we don't want to be in that place. So, all right, Josh. Josh has been here almost from the beginning. Was huge in writing patents, huge in taking a really cool idea and turning it into something that is a real thing. That is something that, it's called, he's an algorithms guy, which means that here's an idea and he turns it into something that's functional in code. And then then the next step is the productization, and that's where we're focused now with this new VP engineering. Josh is a prof and mathematician. He's at the University of South Carolina. MIT undergrad, got his PhD at UCSD. And fundamentally, he's the brains of the outfit. So without further ado, I will ask him to jump in and start talking.
Thanks very much, Charles, and for everybody joining us today. Yeah, as Charles just alluded to, we've got an approach to, in some ways, an age-old problem, right? You've got huge amounts of data, and you got to put it somewhere. But at the moment, all of this data is hard to reach, hard to see, hard to use, hard to analyze. It's just sitting out on a hard drive getting dusty somewhere. Often, in order to save space and to be more efficient about, everything involved. So that's the communications between live devices and the storage and the storage platters and whatnot themselves. You're going to compress the data, right? This is a sort of classical approach. You compress the data so that you're minimizing the amount of space it takes up when it sits on out in your data lake. But that presents some really serious problems for your CIOs and for throughout the organization to make use of this. As an example, Snowflake is in the business of making these data lakes useful to their owners, and they've got quite the valuation. So this is clearly really valuable to have access to your data. You can't just stick it somewhere and forget about it. The whole point is to be able to use it. Advance. Thank you. All right, so as an example, your boss says, why does this keep burning out? We've got a part, keep losing it. So, let's say you're trying to investigate the problem, and the strategy is going to be, okay, there's some sensor we need to read off of 5,000 dump trucks over 5 years. And, each of the dump trucks has got 200 sensors. And then, well, each of those sensors is generating some absurd number of messages per day. The data that you need is buried in the data generated by more than 1 million machines, and this is translating to over 50 quadrillion messages a day. This is not at all unreasonable. This sort of situation you can see all over industry. But here's the kicker: you've got all this data, but it's sitting compressed on a hard drive somewhere in the cloud, however it's stored. and you can't read it. Well, you could read it, but you'd have to pull it all out, uncompress it, and then start looking for what it is that you need. Maybe it's just this one temperature sensor somewhere is the thing you're looking for. It's really like saying needle in haystack is a understatement.
Yeah, and talk about like what somebody would actually do if they got this assignment. What are the steps they would undertake, and how long would it take them?
Yeah, so first you walk over to the storage department and say, hey, I need access to our data lake, right? It's not something that you're normally connected to. And once you've written the software to connect to it and search through it, you've got to start pulling out the huge chunks of data one at a time. They're going to have to be shipped over wires or maybe by truck, depending on what you're doing. And then decompacted, decompressed, and then you're gonna have to search through them, right? You're just looking for that one sensor on that one day that's got some kind of weird setting that where something's been triggered that indicates attention is needed, and you're just gonna linearly search through all the data. There's no way to do it other than decompressing everything, which is an enormous undertaking, both in terms of the amount of data that you have to move around and the amount of processing required. This is enormously time consuming. It takes a tremendous amount of power and labor to make it happen, because decompression is, while it's a very standard thing to do, it's time consuming. And before you do that, the data is totally opaque. So you decompress your chunk one of data, and then linearly search through where it wasn't there. On to chunk two, and 5,000 chunks later, maybe you find the thing you were looking for. So it's really hard to access this kind of data that's compressed and just sitting there at rest in a essentially unusable form. A substantial amount of processing is needed even to look at it, let alone follow up on what you found. Maybe you find that one sensor. Now you have to find every occurrence of that sensor's malfunctioning state throughout the data lake. There's just an undertaking that's completely prohibitive, to the point where organizations have these data lakes that are just not being used. It's sitting there and is not useful to anybody.
Right. And, maybe talk a little about like a genomic research site, because I'd mentioned that before to guys, and I think you could elucidate it much better.
Yeah, this is a great example of this sort of problem that we've heard reports from people in the field of this issue coming up for them, that there's a genomic data is being collected, or whatever kind of macromolecule information is being stored, whether it's amino acid sequences or your nucleotides, lots of different kinds of data that they've got, but it's mostly linear structure of some macromolecule that's used for information storage in a biological context. Organization has all this data, and they've again put it out into a data lake somewhere, into the cloud, into a warehouse, whatnot, and compressed it all because it's just absurdly large. But one day the lab notifies you that there's a particular sequence that's needed out in that lake somewhere. There's this some organism's genome is out there and you need it. Well, how are you going to search for it? This is again one of these problems where you're going to have to go chunk by chunk, downloading the huge troves of data from the data lake and uncompressing it, and then searching through it to find that one genome that you needed. And then maybe again following that up with another 1,000 operations where you're looking to search for that particular genome so that it can be used for whatever the application is at the moment. This is something that essentially all bioinformatics and any serious shop that's doing bioinformatics has this problem where there's just a glut of data that can't be stored on site, and so you've got it in some off-site data lake, but then it's inaccessible.
Okay, next. Oh,
So yeah, this
yeah. Go ahead.
no as I was saying, right, like the it's a huge waste of time in that the user, the analyst who should be analyzing, isn't looking for, maybe you don't even know the particulars of which genome it is. You just know that there's one out there and you have to search them for similarity to a particular sequence or something. That's the hard part, the intellectual hard part. Unfortunately, that's not actually where they're spending their time, right? So 20% of their time maybe is spent on that analysis, on the thinking and the exploration bit, the visualization, all the things that come with research. Instead, 80% of the time, they're just trying to get the data in a usable form, trying to download it to a local accessible site, decompressing it, preparing it for searching, and for whatever analysis you plan to do. It's enormous waste of time, and mostly this data is just sitting out there rotting and is not being accessed. So we need to get that data that's sitting out in that lake into an accessible format so that it can be analyzed and used.
Yeah, and you think about, I got to tell you, when I saw that statistic, I was shocked. I mean, sometimes you'll find it's 70 some percent, but 80% is pretty frequently cited as like a standard. And these are based on real surveys of real analysts and what they really do. And you think about like how much time is wasted. It's phenomenal. So, ta-da. All right.
Compaction. So we've got a solution for this. And it's really novel. There really isn't anything like it out there. So there's a couple of different things going on. And one of them, to some extent, resembles a kind of patchwork solution that people have attempted in contexts where you've got this enormous amount of unsearchable data because it's compressed, which is to provide a kind of index to the data. So we can build indices, a kind of fingerprint summaries of the data that allows you to very quickly search for where the thing you're looking for might be. So this is to narrow it down to a short list of options. If we're talking 10 million files out there you're going to have to search through, maybe this gets it down to 10,000. So once you've got your option, by the way, that's a hard problem, having a useful index. Actually, as just an aside, there's essentially a full version of Wikipedia one can download. I believe it's called DBpedia, that has the entirety of everything you'd find on Wikipedia. But you can imagine that's enormous. So if you want to use it, well, how do you find the one page you're looking for? There's an index. The index itself is enormous. And it's just a list of which file has which item in it. A really low-tech solution to this. We've got a way to do it that is more of a summary, that is itself searchable, isn't just this index, that allows you to narrow in on a small subset of the data that is candidates for where the thing you're looking for actually lives. Now, at this point, you've got it down to, let's say, 10,000 of these enormous files that are compacted. Well, how are you going to read it? Traditionally, it's compressed. You're just going to have to decompress each one and linearly search through them one at a time. Well, with compaction, that's not necessary, because strikingly, this is really where compaction differs from compression, at least in this respect. The encoding is local, which means that the data can be searched as is, in situ, in compressed form. It's compacted, but you can still search through it for search strings or patterns that you're trying to match. That's not possible with compressed data. If you have a compressed file, there is literally no way to search it for a particular name of a sensor, timestamp of a reading, genome sequence that matches a set of genomes you're looking for. It's just not possible. You have to decompress the entire thing and then read through it. But with Atombeam Compaction, you can. Because of the design of the protocol, it's possible to search the data in compacted form and then read it essentially instantaneously at the points where you're looking for the data. So for example, if you're looking for a sensor that's got a particular timestamp because you want the data that's associated with that timestamp, well, you can search the data for that timestamp and then just start reading right at that point. It's not possible with compressed data. You have to decompress the whole thing and then just read it as if it's a normal file. So this makes the entire data lake readable, just like the original data. So all of that dusty data sitting out on those servers is readable whenever you like. And you don't have to download it chunk by chunk and then decompress it and try to find the thing you're looking for. You can just reach out and scan it for the data you're looking for, as is.
So talk about, like, you know, real world terms. Okay, I'm back. You go back and think about the analyst at Caterpillar who's got to figure out, like, all right, I got this part that's overheating. What does he do that's different?
Yeah, so instead of this long, arduous process of downloading, decompressing, linearly searching, and then repeating the process 10 million times, instead, well, there's a few sort of versions of this that we're working towards. One is you start searching the data. So we do have a working version that can search data in compacted format for, let's say, the temperature reading. You know there's a high temp reading somewhere. You know it's a number in some range, and that there's the tag in that field. Let's say it's a JSON file, and there's a key value that says sensor, temperature, and then the number after it. You could just start searching the data for that immediately. Soon, we will make this completely transparent to the user as well. So at the moment, you need to load up the tool that we've built to search the data in its compacted form for the string you're looking for. Soon, you will simply search the same way you'd search any data, but the operating system or the database interface or whichever kind of interface there is to the between the user, the analyst, and on the other hand, on the in the lake itself, where the data is sitting, we'll have it'll be transparently recognized that, oh, this data is the stored compacted data. You just ask for it to be searched the way that you normally would search any kind of file store. And behind the scenes, the operating system, or again, whichever interface it is, but let's just say the operating system IO mechanism, will engage Atombeam's search API instead of whatever search API is typically used for searching your hard drives.
So Khalil, anything you need us to directly answer now? Or
Yeah, we have a bunch of questions coming in. We can continue going through the slides and we can just answer all the questions at the end.
all right, sounds good. All right, so how big of a deal is this?
I mean, it's huge. This takes these unusable, rotting data lakes that are essentially every large organization has this, and turns them into something that you can actually access and use. It means that all of these companies will, for example, be able to passively search them. Maybe you've got something you'd like to do. If only you could read your data. If only you didn't have to go pay somebody to carry giant reels of tape onto the back of a truck and drive them to headquarters. This is a huge obstacle to be able to make use of your own data. We're not even talking about the immediate need. Oh, you realize that there's a temperature sensor. You got to find out which sensor overheated. Okay, there's an immediate need. But there's all kinds of things this opens up. If you were able to think about, how do I use this data? Because now it's actually accessible. That makes all kinds of operations possible that previously were just off the table because the data is unusable in the format that it's in. So this of course needs to be, I was talking about integrating this into file system IO and database access. This means productizing the whole system, of course, that Charles was talking about earlier, making this in a software as a service that we can get into users' hands and make it easy to deploy. But we also need to take these search capabilities, this live reading, random access of compacted data, and turn it into a usable product. And that means integrating it into the file IO, integrating into the database interfaces, and search engines, whether that's your local data search or in the cloud. We'll need to customize this for some different contexts. So I mentioned earlier this the idea of using an index or tags to access your data as summaries so that it's searchable. And you can very quickly identify where the data is that you need. There's different versions of this depending on what the data looks like. So whether you've got a mountain of log files, telemetry, genomics, these all require a slightly different version of the indexing system, but they're all doable. You can provide this kind of summary data to really be able to access quickly wherever the data is sitting in the lake.
The tag would trigger use this code book kind of thing, right?
Yeah, so that's one possible aspect of it. It's where is the data, and in what format is it? So which, for example, like you're saying, that which code book corresponds to this chunk of data. Yep. So well, that's good. So yeah, there's just the building this into a product is, of course, follow up to having the fully mature SaaS product, but this is something that we're currently working towards. So just quick
gears a bit, right?
Yeah, it's a bit of a switch here to we just want to talk a little bit about some of the protocols that we're thinking about and that we interact with in various ways. So this is not something that you're normally encountering, even though you're using it every single day. Protocols are the language that all of the communications is being expressed in. You can't just push bits across a wire. It has to be wrapped in a format that allows the devices on both ends of the communication to make sense of it. So there's a standardized way of formatting and of acting on data so that the communication is possible between the end devices. The most common that you've probably heard of, TCP/IP. This, of course, is fundamentally about reliability. It was designed so that you have recoverable communications if there are errors, and the whole internet is built around fault tolerance. So that's fundamental to TCP/IP protocol. But as the slide mentions, it's got some problems because it was designed for reliability and not speed. And it was designed a long time ago. It's got a lot of baggage it carries around with it. One of the the items that is most relevant in this context is that the headers are 40 bytes long, or they can be and often are. So, any data, if you've got, for example, let's say your little sensor readings are 10, 20 bytes a piece. Well, if you put them in a wrapper that's 40 bytes long, you just tripled, quadrupled their length. It means that it burns up any bandwidth benefits, any storage requirements are being just multiplied in a really prohibitive way. There's a related protocol, MQTT, that is much more recent than TCP/IP and is increasingly the name of the game in IoT data. It's designed specifically for speed because it's mostly being used in machine-to-machine communications. Here, the headers are really small, so much smaller. We're down to 2 bytes, the idea is while we can compact any kind of payload, TCP/IP or otherwise, we're really good at Atombeam is very happy about working in an MQTT context because then you don't pay the price of this enormous header, and it means that with MQTT, with compaction integration, you're able to take your data, compact it, pack it into a MQTT packet, and ship it off immediately, thus preserving all the benefits of Atombeam Compaction's low latency, and of course the data reduction that is really fundamental to our value prop. Another related kind of a protocol, it's a different animal in some ways than these other two, but protocol buffers, or people just say protobuf often. This is very, very fast. The idea is that you can customize. It's something called serialization. It's a custom way on a per data format basis of reducing the overhead of various kinds of formats. So if you imagine your JSON file, it's got all kinds of for example, the commas and colons and curly braces. That's just wasting space, right? It sounds like it's not much, but actually your JSON files are probably more of this formatting business than the data itself. So protocol buffers takes that stuff and whittles it down to tiny tokens that are minimal. The idea is that in some ways it's related to what we're doing at Atombeam, because you're taking deterministic structure and filing it down to a minimal set of tokens. Atombeam takes a broader view of things where we're taking deterministic structure and reducing it down to a minimal set, but also to statistical structure. So the idea is like protocol buffers is not trying to take advantage of statistical repetition, things that happen often but maybe are not guaranteed properties of the data. Atombeam can take advantage of both. So this is something that we can work with protocol buffers to take advantage of sort of both sides of it, the deterministic structure on the one hand and statistical structure on the other.
Great, thanks. So this is a quick little video. I tell you what, we're going to skip it because we're tight on time. And I'll just give Josh the floor here he was going to talk about something that relates to the last one we had, and that way we can handle some of these questions that are piling up.
Yeah, so I just want to talk a little bit about neural computing and neural compaction and what this means for Atombeam in the near future and the more distant future. You may have heard that the world is being changed by neural models, neural computing, and neural networks. So NN is the abbreviation that's often used. The idea is that you can train a machine to act like a brain in a lot of ways. So you're taking an absolutely enormous function space of possible neural behavior and whittling it down to something that models your data by feeding it a huge amount of data. This has been just mind-blowingly effective. ChatGPT is fundamentally a neural model. It's changing everything, right? This is really at the heart of the machine learning revolution. Well, at Atombeam, we want to take advantage of that. So there's a couple of ways that we can use, and I'm sure more ways we haven't even thought of yet. We can use neural computing to make Atombeam better at its job and make it more applicable to new scenarios. One of them is to improve on the training process. So we are getting close to the Shannon entropy bound with our current training process, but there's more room. And for some
maximum, you can reduce the size of data too.
That's right. Thank you. Yeah, there's a sort of fundamental speed limit that Claude Shannon provided back in the 40s to how much you can abbreviate data before you start losing bits. And so because we're mostly lossless, we're bound by that constraint, the Shannon entropy bound. So the idea is that we're close, but there's always more room, and we, by learning more cleverly from the training data, this could allow us to get ever closer to that bound. We could also use neural computing to improve on performance. It's all the rage these days to use neural nets to design your system. So it's the computer designing computer all the way down. So the idea is to use neural computing to improve on Atombeam's latency, on its performance, on its memory profile, and of course my hobby horse, getting close to the entropy bound of Shannon that I mentioned earlier. So at the moment, we've got a project that was discussed last time of marrying neural compression, which is a hot area of research these days, with Atombeam technology. This can go in a number of directions. Just to point out one of them, there's when you're using a neural network, there are millions and millions of numbers being passed around, the activations in the neural network. This is essentially when each of the neurons lights up, it is notifying other nearby neurons of, here's how much I've lit up, the activation. That information that's passed along, the activations, they're not completely random. There's a probability distribution to them that's not uniform. That means that it's compactable data. There's some abbreviation that can be done. And if you could integrate Atombeam into the GPU doing that computation, you could accelerate everybody's neural computing. All of the neural networks operating all over the world could be doing their job faster and more effectively if they had Atombeam inside, if we were able to compact the activations during the training and then runtime process.
Good. Here's your fancy ending. And so what I'd like to do now is ask Khalil to serve up some of his questions, please.
Definitely, will do. The first question here is from Miguel. How can I bring Atombeam to someone that works with data? Is there a brochure? This would be a very big pharmaceutical company.
The answer is yes. We do have a brochure. I would love to have the conversation. I don't want to have the conversation earlier than have it in like to say, okay, I can push my data directly into AWS now or Azure. So do this, send me an email and then we'll talk about it. Charles@atombeamtech.com. And I appreciate that. Yes. We have been approached also by Pfizer and Roche historically. But we really, the focus has been IoT up to now. And so, but you've got to make sure that you can really address what their need is. And so that's where we're focused now. That's not to say we wouldn't be interested in having a conversation at all.
And how do you go from standard compacted data lake to a Atombeam compacted lake?
Yeah, this is really, what I was talking about with integrating Atombeam API into File IO or whatever the database interface is. We want it to be transparent to the user, right? So the idea is that under the hood, when you go to access compacted data, there'll be an encoder and actually decoder in this context, that is being activated. And then the search mechanism that we're talking about as well is it will be deployed then to find the data you're looking for. So the idea is to integrate it into whatever API, whatever sort of interface is being used to access the data.
And can the language of the discussion be more in plain English and not exclusively in technological jargon? What new developments has Atombeam been up to? Any new companies / agencies signing up? What is the latest growth forecast, etc.?
Right. Okay. Yeah, fair enough. This is a technology company, and so we really don't have much choice on that. But, so I would say this, that, we have any number of companies that are approaching us all the time. And what I want to be able to say is, here, go to AWS, go to Azure, sign up, and you're good to go. I need to have that. My feeling is, and I think this is shared by everyone at Atombeam, is the productization, in the sense of having a SaaS product that's available, ready to go. All I need to do is say, here, I'll send you a link and you're ready to go. When we have that, then, the world's our oyster. I can name a dozen big companies that would go right to it and start, I think, probably start signing up and using it. But I don't want to run around and add more. I'm a big believer in partnerships. But I got to tell you, the other thing is, when you have a tiny staff, you can't have people distracted. We have to focus on getting revenue rolling. And how do we do that? By focusing on the SaaS product and getting into the market. So, yeah, of course, yeah, we're talking to, I don't know, this is a giant Middle Eastern oil company. There's any number of companies that approach us constantly, but I want to have a product that I can hand over and say, here, go, use it.
And we are coming down to the wire here. So if your question doesn't get answered, please email Charles directly. So
or post it on the Start Engine site, because that helps everybody. And I encourage everyone to, unless you have a specific thing, go to the Start Engine site and post your question, because, then everybody gets the advantage of it.
Right.
In the discussion section.
For the same
on the video, go to our YouTube, Atombeam's YouTube site, and you'll find the video. It's kind of a demo that you can run, and it walks you through, and you can actually see the real data move and everything.
This question is, I think you'll love this one, Charles. Charles, is your other job being an actor on NCIS Los Angeles?
That is supposed to be a secret. Come on, no. Yeah, actually, you do a lot of this stuff, and you start to get used to it. Anyway, but thanks for that question. Good question. Thank you.
Then we'll answer one more. For the same size data lake, how much storage does compacted data uses versus compressed data?
Yeah, so it varies wildly depending on the data type. Apologies for the technical jargon. It depends in essence on the entropy rate of the data, the predictability essentially of the data. So if it's just random noise, literally, coin flip 0 1s, nothing can be done. The compacted data is equal to 100% of the original data.
Or compression too, same thing. Right?
Absolutely. That's the thing, is that this is getting to Shannon's limit. There's just like the light speed, there's nothing you can do about it. But if the entropy rate is lower than that, then there's something to be done. And so we've tested on, you can't imagine how many different kinds of data we've tested against. And ASCII data usually is very low entropy rate, and we can punch it down to 10% of its original size sometimes. Genomic data has a tremendous amount of patterns in it, and we're knocking it down by 80% sometimes. This sensor data, this sort of telemetry, lots of patterns there. We see 3/4 reduction in size as a matter of course. That sort of, in fact, we tend to tell people expect 75% because that's typical.
And it's comparable in most cases to what compression would get. In some cases better, in some cases a little less. It just varies. And not only that, with some of the improvements that Josh is working on, we could end up being a lot better. I mean, I don't want to promise anything, but there are definitely things like the neural net that could significantly improve that.
Yeah, and one thing to keep in mind is that we're training our engine on your data, right? The user's data is the source for training. So that means that you're compacting in a way that's aware of the data and what it looks like. So yeah, we can get a lot more bang out of it than a general purpose compression algorithm that is waiting around to compress absolutely anything.
Yeah.
Well, gentlemen, that is our time. Charles, I saved all those questions that we couldn't get to today. So I'll forward that to you right after this.
Yeah. Yeah. And if I can, maybe I'll figure out a way of posting some answers to stuff.
Yeah, we can create some content around it
on the site. Yeah. All right, good. All right. Well, thanks everybody. Really appreciate your taking the time to listen. I think personally, this whole searchability thing could be our biggest value. I know it's like, what are you talking about? It's supposed to be so great and all that stuff. I'm not saying reducing the size of data in real time and being able to address any size datagram, any of that stuff isn't really significant. But what I'm telling you is what the average CIO pulls their hair out all the time about, and what's a huge problem, and as Josh says, all this data just sits there and rots. I mean, what good is having all this data if you can't use it? So bottom line is, I think this is a huge deal. And we could license this to Snowflake, to IBM, to Oracle, to Microsoft, to everybody and his brother, if we just build it out and productize it.
Thank you, everyone. Hope everyone has a good rest of their day and have a great weekend.
Yep. Thanks, everybody.
Thanks.
Take care.